Okay, we've been given this model of how particles are arranged in a solid, and we have to state two ways in which this model fails to accurately represent a crystal of sodium chloride. Okay, well, you need to know what a crystal of sodium chloride looks like. Nothing wrong with drawing it. In fact, I would encourage you to do a quick little diagram. In sodium chloride, the chloride ions are bigger than the sodium ions, okay? So it's going to look something like this. Sodium there, then chloride, sodium, chloride, sodium, chloride, sodium, chloride, sodium, chloride, okay? So the first thing that's wrong with this is that the ions are not drawn in different sizes. The second thing that's wrong with it, for your second mark, is that it's not drawn in 3 dimensions. So that's it, those are the 2 marks. The ions should be different sizes, so chloride is bigger than sodium, and this doesn't represent a crystal of sodium chloride because it's not 3D. So let's try and draw this in 3D. If we do something like that, and then sodium there, chloride there, going back like this, chloride, sodium, chloride, sodium, then we can sort of show the 3D structure like that. Okay. Chloride, sodium, chloride, sodium, sodium. There we go. Looks sort of 3D, doesn't it? Okay, let's move on. Magnesium oxide has a melting point of 2852 degrees C. Explain why magnesium oxide... Did I say magnesium chloride? Anyway, it doesn't matter. Magnesium oxide has a melting point of 2852. Explain why magnesium oxide has such a high melting point. For 3 marks. Okay, we've got to extract 3 marks out of this. Right, so what is magnesium oxide? So a change of colour. Well, you need to know that magnesium oxide, like sodium chloride, is an ionic compound, okay? And it's got the same structure. So it's going to be magnesium, oxygen, magnesium, oxygen, magnesium, and so on. Exactly like this, okay? The magnesium is bigger than the oxygen. So like this, and so on, and so on. Again in 3D. The difference is, in sodium chloride, the chloride has a -1 charge and the sodium has a +1 charge. Here, the oxygen has a 2- charge and the magnesium has a 2+ charge. Okay? So, the first thing to write is that magnesium oxide is an ionic compound okay, and that the magnesium has a 2+ charge and the oxygen has 2- charge, okay? At this stage, we're aiming for 3 marks. We're just regurgitating your knowledge, okay? Right, you could also say that that's a cation because it's positively charged and the oxygen is an anion. Might get an extra mark for that. Okay, next thing is, you said it's an ionic compound. It has ionic bonds, which are very strong. Okay? Therefore, you need a lot of energy to break these bonds. break these bonds. And therefore, the melting point is high. Therefore, high melting point. Okay? That should get you the 3 marks. Good. Next question. Write the balanced equation for the reaction of calcium carbonate with hydrochloric acid to form carbon dioxide. 3 marks, curiously, so suggests this might be a bit of a challenge. Well, let's find out. Okay, so they tell us that calcium carbonate, when reacted with hydrochloric acid, forms carbon dioxide. But if you know your chemistry equations, you kind of should know this, because calcium carbonate is, well, it's a carbonate. And when you react a carbonate with an acid, you always get a salt, water, and carbon dioxide. Okay? So if you didn't know that, then learn it now. Very important. Okay? So a carbonate, this is the general case, carbonate plus an acid goes to a salt, water, salt plus water plus carbon dioxide. Okay? See, a carbonate is a type of alkaline or base. It's an acid-base reaction, an acid-alkaline reaction. So it's acid plus alkali goes to salt plus water plus CO2. Commit that to memory right now. All right? And that's what we've got here. Carbonate is calcium carbonate. CO3 means carbonate. The acid is HCl. So we're going to get salt, water and CO2. Well, CO2 is CO2. Water, I hope you know, is H2O. So what's the salt? Well, what have we not used up yet? We haven't used the calcium. That's got to be involved. And the chloride. So it's calcium, actually calcium Cl2, because each Cl, each chlorine, is a chloride actually, because each one has a -1 charge on it. And there's 2 of them, and the calcium has a +2 charge, so that balances. So that's the equation. Now we've got to balance it. So, what have we got? 1 calcium on the left, 1 on the right, looking good. 1 carbon on the left, 1 carbon on the right, looking good. 3 oxygens on the left, 1, 2, 3 on the right. This is looking good. 1 hydrogen on the left, 2 on the right. Okay, so we'll have to try putting a 2 there and see what happens. Okay, the calcium, 1 on the left, 1 on the right. Carbon, 1 on the left, 1 on the right. Oxygen, 3 on the left, 3 on the right. 2 hydrogens on the left, 2 on the right. Now there's 2 chlorines on the left, but there's 2 on the right. So it's balanced. And that's it. Okay, that gets you 3 marks. Not too bad. Good. Okay, next question. Thermal decomposition of copper carbonate. I'm going to have to clean the board. Okay, so we have thermal decomposition of copper carbonate. So all we're doing is heating it, and it's decomposing into copper oxide and carbon dioxide. Okay? Right. Now, we're told that 15 grams of copper carbonate is decomposed. Right. It's working out moles and masses on the left side of the equation on the right, that type of question. Do these sort of questions like this, okay? Write in columns underneath each one everything you know about it, okay? Follow this system and you won't go wrong. Right, so 15 grams of copper carbonate. So write that underneath. We've got 15 grams, okay? Calculate the mass of solid produced. Well, that's the gas. So it wants the mass of this produced. So that's our target, okay? Right, it tells us relative atomic masses. Okay, so carbon is 12, oxygen is 16, and copper is 63.5. Right. So that's it. That's everything we have to go on. So like I say, in columns underneath, write everything you know about it. Now, from the relative atomic masses, we can write the relative, or the molecular masses of these. So that's the next thing to do. So we've got copper carbonate. So for copper carbonate, the relative molecular mass is the sum of the relative atomic masses. So it's copper, 63.5, plus got 1 carbon, that's 12, plus 3 oxygens, that's 3 times 16. Okay? Do it in your head if you can, or stick it in a calculator, and that turns out to be 123.5. 123.5. Now, units is grams per mole, right? So copper carbonate weighs, this is the relative molecular weight, it weighs 123 grams for every mole. And write it like that as well. Don't write it at an angle, grams per mole at an angle. Write it like this for reasons we're going to get to in a minute. Good. So that's that. So write it underneath in a column. 123.5 grams per mole. Okay? Now, copper oxide. So copper oxide. Copper is 63.5 plus 1 oxygen is 16. And that comes to 79.5. Oh, 79.5. And include the units, grams per mole. Okay? Now, when you have 2 of these things in a column, you can work out the third by looking at the units. And this is why I say include the units and write them like this. Because if you have something in units of grams and you divide that by something in units of grams per mole, okay, look at the units. You end up with something that has units of moles. So this is what you want to do. In any of these columns, as soon as you have 2, immediately work out the third. There's 3 things. There's the mass, that's grams. There's the molecular weight, that's grams per mole, and there's the moles. So we have 2 things, so therefore we can work out the third, which in this case is things with moles. And by looking at the units, I know that if I divide that by that, you've got grams on the top and grams on the bottom, so they cancel. And when you've got something that's dividing and dividing again, this is why I think about it, then that thing flips up to the top. And you've got something in units of moles. Okay? So do 15 divided by 123.5 in your calculator, and you get 0.12145 something something something, but it's in units of moles. Okay? And that's how many moles of copper carbonate we have. So write that in underneath. We've got 0.12145 something 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 moles. So they gave us 2 of the 3, if you like. They gave us the mass. They gave us the atomic masses, the relative atomic masses, so we could work out the relative molecular mass very easily. Okay? So they gave us 2, we worked out the third. Good. So we have the number of moles of this. Now, once you've got the number of moles, you can work out how many moles of the thing on the other side of the reaction arrow you have, this thing. And you do it by looking at the big numbers in front of the molecule, okay? Now, the big numbers here are 1 in both cases. There's no number there. In other words, it's an invisible 1. There's 1 molecule of copper carbonate and there's 1 molecule of copper oxide, okay? So that means it's a 1-to-1 ratio, and that tells you the molar ratios. If there's 1 molecule of that to 1 molecule of that, it means there's 1 mole of that to 1 mole of that. So this here, these two mole values will be the same, it's 1-to-1. So we can immediately write down, by looking at the big numbers, number of moles of copper oxide. So you go straight across and we know that there's 0.12145 something 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 moles. Okay? By the way, stick that in your calculator's memory. Don't write all these digits down every time. Just learn how to use your calculator properly. Get it in the memory of your calculator so you can dig it out immediately with the recall button. Okay? So now we've written it in the column and we've got 2 of the 3 things again. We've got the number of moles and we've got the grams per mole. So therefore we can work out the third, which is grams, the mass, which is what we want. So we're nearly there. And again, you know whether to multiply or divide simply by looking at the units. Okay, we've got grams per mole and moles. So if we multiply them together, the moles will cancel and you're just left with grams. So we're going to do 79.5 grams per mole times 0.12145 whatever moles. Dig that out of your calculator's memory to get the exact number. And look, this is what I'm talking about. Include the units and write them down, because then you know whether you should multiply or divide. Moles on the top, moles on the bottom, they cancel. And we're left with just grams. So whatever this is, it'll be in units of grams, which means it's a mass. And that's what we want. So stick that in your calculator and you get 9.65587 something something something, and it wants this to 2 significant figures. So to 2 significant figures, that 5 pushes that 6 up to a 7, so it's 9.7 grams to 2 significant figures. And that is how you should do all questions like this, okay? Write out the equation, make sure it's balanced. In this case, it was already balanced, okay? And then write in columns underneath each one everything you know about it. And there'll always be a column where there's 2 things that you already know. In this case, it was that and that. And then immediately, whichever column you see 2 things in, work out the third, okay? And when you've got the moles, look at the big numbers, and then you can go across from one column into the other by looking at the molar ratio. That gives you this, and then you'll already have 1 thing in that other column, you'll then have 2 things in that column, which means you can work out the third. And you know whether to multiply or divide to get what you want by looking at the units. Always include the units, okay? And that's how you do these sort of questions. Right, more board cleaning and then the final question. Okay, so we're told that magnesium reacts with 2 water molecules in the form of steam. Actually, it just means it's a gas, but that's not that important here. And we get magnesium hydroxide and hydrogen. Okay? They tell us the relative atomic masses. So hydrogen is 1, oxygen is 16, and magnesium is 24. Okay. And we have to show that the law of conservation of mass applies. Okay, they tell us that we have 2.4 grams of magnesium, 5.8 grams of magnesium hydroxide, and 0.2 grams of hydrogen. Right, so how are we going to show that the law of conservation of mass applies? Well, we have to show that the mass of water that reacts with magnesium is such that when added to 2.4 grams, it will equal these two added together. So 5.8 to 0.2 is 6 grams. So we have to work out how much water there should be here. And if we do it correctly, it should be 3.6 grams, because that would add up to 6. Law of conservation of mass in a chemical reaction: the mass of the reactants always equals the mass of the products. So mass of what goes in must equal mass of what comes out, total mass. Okay, so we've got to find the mass of water that reacts. So same principle as the previous question. Write in columns everything you know about these things underneath. So they've given us the masses, so we have to work out the relative molecular masses of each of these and write that underneath. So magnesium, well that's easy, it's just magnesium, it's 24. So it's 24, include the units, grams per mole. Okay? Right, water, H2O. You don't need worry about the big number, okay, when writing down the relative molecular mass here. Ignore the big number for this bit. It's just the molecule, okay, just H2O. Don't worry about the big two. So it's H2O, that's 2 hydrogens plus an oxygen, which is 16, so it's 18. Okay, 18 grams per mole. Right, now we can work out the mass just from this, but just for completeness' sake, to get you in good habits, we'll do it for these two as well, although it's not strictly necessary. So magnesium hydroxide, that's going to be 24 plus 2 oxygens is 32, 2 hydrogens is 2, that's going to be 26 plus 32 is 58. Okay, so 58 grams per mole, and H2 is just 2 grams per mole. Okay, like I keep banging on about, write everything you know in columns underneath them. That's one of the keys to success. Right, so we've got to work out the mass of water that's reacting. Well, like I said, if you write down everything you know, in one of the columns there'll be 2 things, and therefore you can work out the third. So now we know the mass, and we know the molecular weight, which is the atomic weight in this case, because it's just one atom. So we can work out the number of moles. So look at this, look at the units. If we divide 2.4 grams by 24 grams per mole, write down the units, include them. We know that if we divide that by that, something with grams divided by something with grams per mole, grams on the top, grams on the bottom, they cancel, moles flips up to the top, and we've got something in terms of moles, which is what we want. So 2.4 divided by 24 is 0.1. So we have 0.1 moles of magnesium. Okay. Now we can work out how many moles of this we must have by looking at the big numbers. We've got 1 magnesium, invisible 1 there, and 2 waters. That means there's twice as many moles of water as there are of magnesium. So therefore we must have 0.2 moles of water. Okay? No calculations necessary. From going from one column to another, you look at the big numbers to work out the molar ratio. It's 1 to 2, 1 to 2. Okay? So now, like I promised you, we've suddenly got two things in this column, so you can work out the third. We've got grams per mole and mole. So, if we do 18 grams per mole times 0.2 moles, okay, we've got moles on the top, moles on the bottom, they cancel, and we're left with just grams, which is what we want. So, 18 times 0.2, well, 2 18s is 36, so it must be 3.6 grams. So that equals 3.6 grams. Okay? So we've done it. We had to show that that plus that equals that plus that. So just finish it off neatly by saying 2.4 grams plus 3.6 grams on the left equals 6 grams, which also equals 5.8 grams plus 0.2 grams. We have indeed shown that conservation of mass worked or applied and is correct in this question. QED. Boom.